Now let us go into our SVM classification method. We have already seen the theory of SVM, where it is a classifier which can be used for either a linearly separate as a linearly separable data. If it is non-linear, I can increase the dimension by using some kernel trick, and then I can actually work. So how my separation should be there actually is I should draw a margin, and the margin should be as large as possible. That is, what is margin is nothing but a particular position where if I keep 2 points, the distance between the 2 points in two different classes should be as large as possible. That I call as margin. Second comes the kernel trick, where if I want to increase the dimension, then I can actually change a nonlinear data to a linearly separable data. So that is what we will be doing with respect to the kernel, right? As I already said in the theory class, there are many ways of applying kernel, and we are going to see that practically in this particular session, right? We also have gamma. We also have the overfitting criteria, right? By using the regularization techniques. See, right? Everything will be using it and will be solving the same, right? Yes. So what is this data set? If you remember, this is actually taken from our decision tree classification data. We have pre-processed this data for match result prediction, right? We have got winner, ground, host, opponents, match result, everything. This was the data which we used for the decision tree algorithm. We already solved decision tree for match outcome prediction in the previous laboratory class. In that, we actually pre-process this particular data to zeros and ones. This particular same data, I'm going to apply for the SVM classifier. My decision tree is giving me around 0.63 percentage accuracy. Random and Bayesian actually is actually 0.5 something. And when I used random forest, it gave me 0.65. And now let us see what will be for the support vector machines, right? Yes. Now I'll import the necessary packages here, right? So import pandas as PD, import numpy as np. I want matplotlib. So import matplotlib dot plot as plt. Next inline execution of matplot visualization. So I'll include that matplotlib inline. Now let us now these are the necessary packages we actually require with respect to the data set reading. Then I'll be including from the scikit-learn package, I'll be including the SVC package. So that and all will be used when it is actually required, right? Now let me read the data set. Data is equal to td dot read underscore csv, double quotes, click one, I think it is available. Click one dot csv, right? Now I print the data. If you see the data, actually we have one extra row printed here. Why? Because when I create our own data by using program, we'll be having row indices automatically created, right? Row index. So this row I have to delete. First we will see how the data actually looks. See, this is how the data actually looks. I want to remove this unnamed row because each time you create a thing. Now if you see, for this particular column, row is automatically is created, right? So what I can actually do is I can actually delete this particular in the entry, right? So what I can do is data is equal to data dot drop off this particular column. I'll take copy this particular column. I'm going to delete. In the double quotes, I say this particular column need to be deleted. It is given as unnamed zero. Why? Because I didn't give any column name for this. So I put it unnamed. It was actually present as unnamed zero. And I need to delete this particular entry, whether it is a row-wise deletion or column-wise deletion, I have to say. So I specify axis equal to 1. If I specify axis equal to 1, it means that I'm going to do a column-wise deletion. If it is axis equal to 0, it means row-wise deletion. So I need to delete this particular column. So I make axis equal 1. Yes. So I'll execute this. Then this data dot head, I'll print it at the end. Yes. I get the data ready, right? Winner, ground, host, opponent, and match result, right? If needed, I can also study the shape of the data. Data dot shape of the data dot shape. Yes, 921 rows are there with 5 columns, right? Now we'll go on to the subsequent item. So, yes. Now let me fix what is the inputs and output. Fix the inputs and outputs. So what is my input variable x is nothing but I'm going to have the winner, ground, host, opponent, everything as input and match result as the output variable. So what I do, data dot drop off match result. You drop the from the entire data, you drop the match result alone, and the remaining things what are available will be considered as x. X is equals 1 because you remove this particular column alone. Remaining all fours is given as x. And what is y? Y is nothing but data of match result alone. Match result. This alone is x and y. Now I have taken my input and output. Then what I'll actually do, let me run this particular cell. This run. Now we need to split it into train and the test. So I'll use from sklearn dot model underscore selection import train underscore test underscore split. Now x train, y train, x test, y train, y test is equal to train underscore test underscore split off. I can specify what is my input. Input is x, output is y, and what is the test size. Let me fix the test size to 30%, 0.30. I can also specify the random state is equal to 101 or some number. So I have done my training, testing, everything. Sorry, training and testing data are splitted separately. Now we need to go into our SPMM classifier, right? So these are the data that we need actually. We already took the pre-processed data, so we don't need to do the pre-processing again because the data is already pre-processed during the decision tree exercise itself. Same data we are using, so we need not do pre-processing again. Now I have taken X as uh, these particular four columns, that is winner, ground, host, and opponent, and sklearn dot model selection. This particular cell is going to split it into training data and testing data, right? Yes. Now I call the SPM package. Some sklearn dot SPM dot SPM import support vector classification classifier import SVG. So I'm doing this. This particular package is going to contain all the hyperparameters which we can actually train and modify, right? So I do the same. So my first classifier, I'll name it as SV1. By this first classifier is going to be a linear classifier of SVZ. So we are going to see all types of classifiers starting from linear, non-linear polynomial, next a non-linear RBF kernel, and so on. Everything we are going to see, and we will typically identify how the linear kernel, how the polynomial kernel, how the RBF kernel, how the sigmoid kernel, everything is going to differ, and what accuracy each thing is actually going to give for this particular data set. Okay. Yes. So SV1 is equal to the first classifier I call SVC of, let us do the parameter setting. I'm going to act only on one parameter now. Usually SVC has four hyperparameters. One is the margin, which is actually need to be trained appropriately. Next is kernel. Next, my regularization parameter C, and finally gamma. So these four things I actually have. So first, what I'm going to act upon individually is the kernel alone, right? So I put a linear kernel here, and I train my thing sv1 dot fit. I'll take my x train and y train, x train, comma, y train. Let me run it. Yes, it is executing. Now, if you see the degree is automatically set as 3 and the gamma is equal to scale, kernel is linear, right? So we have these many functions actually available as hyperparameters here. Right? Let us proceed into see what is actually the accuracy given by the linear classifier for the match prediction. Right? I take ypred is equal to sv1 dot predict of x test. So I'm going to predict the x test now, and let me include the accuracy metrics here from sklearn dot metrics import classification report as well as the accuracy metric I can take. Classification from sklearn import from sklearn dot metrics import classification underscore report and confusion matrix also. So let me print the confusion matrix. Print confusion matrix of. We'll put the confusion matrix for y test and y predictor. Actual y value and the obtained y value I take. Y test and y predictor. Similarly, the classification report for y test and y predictor. Y test comma y predict. And let me run this. Y pred is equal to sp1 dot predict of x test. So x is actually a capital X. Now if you see, the accuracy is very less, around 60. See the precision value is also around the 60. So surely we need to increase the accuracy terms. Why? Because the wrongly predicted values is totally 32 plus 77. So around 109 data are actually wrongly predicted. So we need to act on it and we need to upgrade it. So this is with respect to the linear kernel, right? I put it here as linear kernel SVM. That's it. So if my accuracy is low, what I can actually do is I can try for some other kernels. Why? Because if I want, I can also visualize and see how the data is being separated. Now, for this particular kernel, my accuracy is not that much to an acceptable level. Why I say it is not an acceptable level is I already know that my decision tree gave an accuracy of 63 percentage, random forest gave up to 65 percentage. So we need some better things also. So it is only 60. So surely SVM can do something better if I change the kernel value, right? So I'll change the kernel value. Let me go into the subsequent thing. Now the same thing I'm going to change the kernel alone. Same code. If you want, I'll do the same thing. I just copy this code. I come to the new cell here. I paste the same thing. Now what I'm going to use is I'm going to use a polynomial kernel. I assume the data is going to be a non-linear. I need to increase the kernel size to a polynomial kernel. So I say kernel is equal to poly. And when I say make the kernel is equal to a polynomial kernel, I can also specify that degree, right? Because how much degree you actually require. I say degree is equal to say 8. Or I can make also degree is equal to 10. A nominal degree 10. Let me execute it. If the degree increases, the execution time also increases. So better I can make it SP2. That is better.
Sir, in previous also degree is 3 na, sir.
Yes, come again.
In previous one also it is degree 3 na, sir. It showed like that.
Yes. In previous one, it shows degree equals 3. That is automatically specified as a hyperparameter here.
But linear na, sir.
Linear in the sense, good question. 1 minute. Because I specified kernel is equal to linear. Let me look into it. I'll open my PPT and I'll see that. Yes, it is actually that it is going to be a linearly separable data, and in a polynomial transformation. Actually, I'm going to apply a linear kernel after transforming it to a third degree. It means that we didn't specify the degree before. If we specify the degree before, it will be degree one data itself. Here it is. If you want to apply linear kernel, the data need to be transformed into degree three automatically. You can also specify it is not the kernel is going to be in polynomial. The thing is, the data is actually going to be in polynomial. I can also directly specify here as degree equals one also, and see. Yes, I can also specify it as degree equals one. It is actually fitting to be degree equal to three by because it is transforming the data to a polynomial and then putting here a linear kernel. That is what the explanation given here. It is a linearly separable data which can be transformed to any polynomial degrees. A linearly separable kernel, right? It is with respect to the data, not with respect to the kernel, right? I am making it clear, Shirdi.
Yes, sir.
Let us run this polynomial kernel. Kernel is equal to poly, and I specify now degree equals 10. And for this, once it runs, I'll use the same thing over here for applying it to the predicted data. We wait for this data to run. So degree equals 10 now, and I'm running it. Good accuracy, right? I'm getting an accuracy level of 67 or 68. Right now, the thing is, the accuracy is increased at degree equals 10. We can also move further and increase the degree to some other higher levels and see how the degrees are actually changing. If it is like the same or it is increasing even more, we have to check. But the problem with this thing is, if you transform the data to higher level polynomials, surely your time will be vanished. So you have to check that also. Right? This is with respect to the polynomial kernel. Right? So I wait for you guys to finish this polynomial kernel. Not much work is there. Just copy it, change the kernel to poly, and give a degree as 10. You can also change the degree to some other numbers and see and check how much is actually increasing this particular level. After some particular limit, it may converge. Right? If I increase this to some 12 or 13, it may converge. Kernel, change the kernel to POL by poly and degree equals 10. And like Shirdi has one thing, I want to try this. I delete this and see and how what is the degree it actually takes automatically. I'll check this. It's taking 3. It means that it depends upon the data. Next, what I will try to do, Shirdi, is I'll give some different data. For this data, automatically what the value is going to be there. Surely, why it is actually taking in the 3D is actually the thing. Since there is going to be a hyperplane, it is taking as a 3D or any other reason we have to check. I'll give some other data also here and check Shirdi. For a different data set, whether it actually changes, we will check and say, right? Because of the hyperplane or some other reason, we have to check. I'll give some other data set. For the data set, if it is taking the default value as degree equals 3, and then it means that it always projects the data in 3D because of hyperplane. Next kernel, what you're going to see is the very famous the RBF kernel, radial basis function. Yes, so by the end, we can actually see a different type of accuracy for everything. Then what we'll be actually doing is we'll be enumerating the points on which particular data characteristics, which kernel should be used. That we'll be seeing, and that we'll be enumerating in some word screen or something so that you can recap and use it for MCQ or some other things, right? So in which particular data characteristics, which kernel should be used? Those things. For example, if it is sigmoid kernel, right? We know that sigmoid is actually closely related to the logistic classifier. So sigmoid in the sense itself, only when the data is highly binomial, then and the equal number of zeros and ones are there, then surely sigmoid can be used. So those if there is more number of classes in the output label, then it means that sigmoid cannot be used. So like that, every kernel has some features so that that particular data having those characteristics or features that kernel can be employed. Right now, I take the same thing. I'll go for SP3 now. So SP3 is going to be RBF kernel. So then let us see it for RBF kernel. So now kernel, I'll change it to RBF and don't work on the degree now. So I leave the degree as default to 3. And I change it to SV2 to SV3. It is setting aside always projecting in the 3D data. Now let us see the accuracy of RBF kernel. I hope for this data RBF will not give that much result. I hope. Let us see because kernel polynomial is giving the result in the sense and it is actually highly sparse. So only polynomial is giving some result. Let us see what is the result from this RBF kernel. 67 almost. Let us see how what is the thing 68. So somewhat closer to polynomial, but polynomial is actually better with a degree 10. But if I increase the polynomial to degree 11 or 12, it may show some other higher accuracies also. So this particular RBF kernel is closer to polynomial of degree 10, right? So this is RBF kernel. So everything will be transforming the data in that in different fashions. Ultimate is I want to put a hyperplane in between and make it separable. For this, RBF will do a different logic. Polynomial will do it in a different way. Linear separable, linear kernel will do it in a will not to transform it. It will directly have the data in a 3D view itself. Sigma it will transform it to some other different fashion and so on. Right. So this is with respect to the RBF kernel. Yes. So the same thing, you copy and paste and change the kernel to RBF and remove the degree. And I'll proceed into the sigmoid kernel now. I take it all. Put it over here. Fourth kernel we are going to see, that is sigmoid kernel. So instead of RBF, that I'll put as sigmoid. That is actually the only change I do. Sigmoid kernel. Sorry, it can be SP4. Yes. So here also see degree is equal to 3. It is always projecting in 3 dimensions. So I'll change here the accuracy. Let us check the accuracy of sigmoid kernel. One of the main features of sigmoid kernel is sigmoid kernel can work only with the two classed output variable. It cannot work on multiple class output variable. It can work only with the two classes. It is a binary classifier, actually sigmoid is. So only we use it for logistic classification. And the accuracy is very low in because it requires both zeros and ones to be equally divided. So equal number of zeros and equal number of ones should be there. Or equal number of wins and equal number of loss should be there. That is, if there are two classes in the particular output variable, then all the classes should be of same, right?